Hello again, class. So we're continuing to fill these tables in. We've got a couple places left to go. So today I want to talk about this lower left square. That is where we're taking indistinguishable objects and putting them in distinguishable boxes. Now, you might recall that we usually think of this as the candy to children problem. I want to give however many pieces of candy it is to however many children, and I want to figure out the number of ways to do that. Okay, so let's review how to do that in the no restriction case. And then once we've done that, then we'll talk about, well, what if we impose the additional requirement that we give each child at least one piece of candy? And what if the parents don't want their children to be kept up at night, and so we impose the restriction that you can give each child at most one piece of candy? Okay, so no restriction first. Remember, the way we do this is we lay out the children in some order. So Alice, Bob, Carol, David, whatever. And then we lay out the candy we're going to give them. So we say, okay, I'm going to give you 10 total pieces of candy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of candy. All right. And then we realize that what we're really deciding is where to sort of draw the line between these. So I'll give Alice the first piece of candy. I will give Bob the next 3. And I won't actually give Carol any. And then I'll give David the remaining 6 pieces of candy. And so we have these diagrams, these dot and bar diagrams, or star bar diagrams, or whatever you want to call them. And these correspond to all of the distributions of the candy. And so in this case, if I was giving 10 pieces of candy to these 4 children, I would be looking at all of the ways to write out this list of 13 symbols. And so really, I'm just going to say, okay, it's 13 symbols, but I need to choose where of those 13 places I put the 3 bars. So it would be 13 choose 3. Okay, so in general, if it were M candy and N children, then how many total symbols would I have? I would have what looks at first to be M plus N symbols, but here's where you have this annoying off by 1 error, because you actually only need N minus 1 bars to separate N children. So in this case, I needed 1 bar between Alice and Bob, 1 between Bob and Carol, and 1 between Carol and David. And so, in fact, this was M plus N minus 1. That's the total number of symbols. Okay. And of those, N minus 1 are bars. So we end up with that as our general formula for the number of ways to distribute N indistinguishable pieces of candy to N children. Okay, so that is what is going to go here, is that. M plus N minus 1, choose N minus 1. Okay, so that was that case. Next up, let's talk about the at most 1 object per box situation. So in this situation, we're again thinking, okay, I'm going to give M pieces of candy to N children, but I can't give any child more than 1 piece of candy. So since really all I'm doing is deciding which children get the candy, then the number of ways in which I can do this is actually just to choose which m children out of the n get the candy, which is to say that this box is in fact just n choose m. This is just our binomial coefficient, which maybe didn't feel like a distribution problem, but in fact lays exactly in the square of this distribution problem. Okay. Last up for this video about distributing candy, we have this indistinguishable, again, the m indistinguishable pieces of candy to n children, but every child needs to get at least one piece of candy. Okay, so there's a couple ways we could do this. One of them is to say, okay, I'm going to go back to this version, and before I even give out the candy, I'm first just going to hand each child one piece of candy. And so instead of giving out m pieces of candy, I'm really giving out m minus n pieces of candy. And then we'll sort of proceed from there. And that's a fine way to think about this. But there's another way that sort of presents itself if you stare carefully at this picture, which is, how do I know from this picture that someone didn't get any candy? Namely, the way I know from this picture that someone didn't get any candy is by looking at this place where I put 2 bars in a row. And so in other words, when I'm asking how many ways are there to do this, I'm really asking how many ways are there to distribute the bars such that 2 bars don't happen consecutively. Okay, that again seems like that's going to be a hard question, but I can think about it a different way. I can think of it as, for each gap between the children, I need to either put a bar there or not put a bar there. Okay. So there's either a bar here or not, a bar here or not, a bar here or not. And there's never 2 bars in any of these spots like there was in the previous one. Okay. How many bars am I going to need? Well, in the Alice, Bob, Carol, David 10 pieces of candy version, well, I'm going to need 3 bars because there's 4 children. And there's 9 places that I could put those 3 bars. So here it would just work out to be 9 choose 3. Okay. But in general, I can make my m dots. So there's my m candy or m dots. I guess a dot is a kind of candy, so you can make it that kind of dot if you want. Please do not go out and buy candy. And so then we need to decide where we're going to draw the dividing lines. And so we just need to decide of each of these possible slots between the pairs of adjacent candy, which one am I going to use? And so that's going to be their m minus 1 slots. And I need to choose n minus 1 of them to be dividers. Okay, so here I'm going to get m minus 1, choose n minus 1 as my number of ways. So that goes in this slot. So this is m minus 1, choose n minus 1. Okay, next time. We only really have 2 boxes left, those 2, but I'll go ahead and talk about that in combination with this box. And so we're going to talk about how the distinguishable to distinguishable case really corresponds to functions. And so we'll figure out what kinds of functions these correspond to, and then we'll finally disentangle what goes in these boxes, and then we will have successfully completed the 12-fold way. Until next time.